Okay, good afternoon, everybody. Hope you are doing good. In the name of Allah, we are going to have the next chapter soon, but before that, let's finish whatever has left from the previous topic, which was the processor. Any questions? As you remember, we've talked about MIPS and how to implement datapaths and how to design the controls. Then at the end, we talked about a little about pipelining, and the single cycle MIPS is not efficient as it should be, because we have to put the clock cycle for the longest pass in the pipe, in the data pass. So it was not efficient, and then we talked about pipelining. Any questions regarding that? Actually, we had two reflections. One of them was about critical path, the other was about pipeline. So we can read them. Okay? So critical path. I ask you, what does critical path mean? Before doing detailed simulation and synthesis, what instruction do you think has the longest path? Which instruction has the shortest path? Why is the critical path important? So let's see who is first. Name, which is not here, I guess. Yeah, name is here. No. Then we have Akachukwu. No? No Akachukwu. Then we have Vince. Those who post soon, they are not showing up. Yeah, showing. Kevin. Yeah, last time I guess it was Kevin. Yeah. So Kevin, what did you write? The critical path in a processor refers to the longest path or sequence of instructions, or one instruction, that takes the maximum time to complete execution within a pipeline. There is no pipeline. We are not talking about pipeline here. And there is no instruction. So two things that you could reconsider, Kevin, okay? Yeah? On the other hand, the instruction with the shortest path is typically a simple arithmetic regime such as add or subtract. The critical path is important because it determines. So I didn't agree completely with the longest path and the shortest path. We could read others, but let's see what you write for the importance. The critical path is important because it determines the maximum clock frequency. Yes, that's good, because it determines the maximum clock frequency that can be achieved by the processor. If the critical path is long, it increases the time taken for each instruction. Here you are writing very good, but here you are writing something else. Sequence of instructions, no. Just one instruction, and it is not a pipeline, it is single cycle processor. If the critical, it increases the time, this is important, the time taken for each instruction to traverse through our pipeline. It couldn't be a pipeline, it could be single cycle, it could be pipeline, it could be multi-cycle implementation, whatever it is. But it is the time that we have before the next clock cycle. Let's say this, before the next clock cycle. Okay, Kevin, good. Mason, here? Mason, okay. Let's see what Mason wrote. The critical path is the series. Why instructions? Yeah, I liked if you write one instruction here. A series of instructions that take the longest to complete. Maybe you mean series of actions.
That's what I meant.
Yeah, not instructions. Because, for example, let's see, do you have example here? The shortest? No, you didn't. I asked you to put the example also. I wanted you to give me an example of what instruction do you think has the longest path. Okay, thus dictating the minimum amount of time for a minimum or maximum amount of time for a command to complete and dictates the clock period. Yeah. I would say that maximum. This is because it is not a very good idea to vary clock periods. It's almost impossible to vary clock periods based on different instructions. The instruction with the shortest path is roughly branch instruction, clocking in at 500 picoseconds. And the longest pass is, longest pass is load. You mentioned that. Load is the longest pass. As the example in the book, it is about 800 picoseconds. Good. One more. Let's say one more to see if everything is written clearly. Christian. Yeah, Christian? Yeah. Yeah, good. You are writing very long, which is good. But I hope that all of the statements would be precise. Let's see. Yeah, that's why I am going to read it. It's good for you also. The first one was named, but which she was not here. Upon analysis of the many critical components in a MIPS datapath, we observe certain properties that are crucial for the proper function and most efficient result of the operation. Okay. Especially for a single cycle processor, we need to take into account that data path, critical path. The critical path here, it is here from here, a property in the data path that's observed as the longest delay path in between state elements in a circuit. Or in other words, the longest instruction, good, not instructions, within the data path. Okay, and the state here, you mentioned state elements, which is good. Typically, in general, it is state elements. But here, in our example, in our case, it is among clock cycles. Because for each clock cycles, we go to the next state, which is the next PC. That's what our single cycle processor does. But if it is a general design, a general sequential design, then the critical path is the longest path in between two states, as Christian mentioned. The longest instruction in the database is represented as the instruction that takes the longest amount of time to compute within a single. Very good, Christian. Hence, the processor needing to take the amount of time minimum per cycle in order to completely compute all instruction in its set. Yeah, I guess minimum, he means that we have to put a clock cycle either at that amount or either more of that. So the minimum clock cycle would be the longest critical path. Typically, the time it takes for the processor to iterate through one clock cycle will be its critical path. Yeah, here it is one clock cycle. Before doing detailed simulation system, we find that the load word, very good, the load. If you do analysis, synthesis, do you know what is synthesis? I guess you have done it in the lab. Synthesis. Nobody? Synthesis? Simulation. You know simulation, yeah? Okay. What is synthesis? Synthesis means making, generating.
It was like compile all the VHDL and whatever. And
okay. To compile to what? To the FPGA. Synthesizing means making the real physical circuit. Because, for example, in your lab, you are using Quartus. With Quartus, you put something as a design. Up to now, you were using a schematic entry. And I guess you had some small VHDL code also, I think so, okay? But from after this lab that we are going to do, you also could have Verilog file to represent your design. After you finished your design, you start simulation. With simulation, you make sure that the functional operation, the functionality is okay, and it does whatever you wanted it to do, the design that you done. After you made sure that everything is okay in simulation, then you synthesize it. When synthesize it, in Quartus it says compile. And if you do compile, you see there are lots of things in the left side, analyzing, timing, synthesizing, floor planning. These things are done in the Quartus. So what it does, it gets your design. You have and or flip-flops, registers, so many things to do. It gets your design. It tries to implement them in the FPGA that you are targeting. So it puts them in FPGA. In FPGA, we have different kind of tools to implement. For example, you have lookup tables, multiplexers, and these things. I don't go to that detail. But at the end, you have something in the FPGA, and you can connect wires to that. You can test it. It is, for example, it is a datapath, a processor. You can get that FPGA, put it in computer, and use it. This is synthesizing, when you do synthesize. Before doing synthesizing, we cannot say what would be the timing. After synthesizing, that everything is placed in the place. For example, in our case, register file has been put in left corner of the FPGA. Then instruction memory is put somewhere else. Then data memory is put. And then we have connection in the FPGA, connect them together. After all of them has been placed, which we call them floor planned, after that, we can see the timing. How long does it take to one operation to be executed? And at that time, we can say, okay, our critical path is this path. It shows you. The Quartus shows you. The Quartus shows you that this path is the longest path, and therefore your maximum frequency, clock frequency could be this, something like that. So that's what I meant, that before synthesizing, what would be your guess, which you told that it is load. Yes, it's good, because in load, we have fetch, then we go to register file, then we go to ALU, then we go to data memory, then we go to writing back to the... So we have everything to be done in load. I guess last time I made a mistake. When I was talking about the longest path, I compared load and a store by mistake. A store doesn't have the write back part, so it is smaller compared to load. Load has the write back in the register file, so it is longer. Okay, so the load word. Instruction has the longest path. This is due to the properties it contains at entities it needs to access upon conduction of things, such as accessing the instruction memory, very good, accessing register file, using the ALU, sending the result to data memory, and then updating the register value. Very good, Christian. This accesses almost every component of the database, hence load word being the longest path. Contrarily, and instruction with the shortest path would likely contain elements that access minimal parts and consist of quick instructions that obtain this. What would be, for example, register, the instruction that best fits is the jump instruction. I agree with you, but I am not sure. We have to do the simulation and synthesizing to make sure, but I agree with you. My guess would be that the jump would be the fastest instruction with the instruction that we have. And register and can quickly, very good. And instruction memory applying its J format of properties and ALU control dependency to quick, very good, very good. That's perfect. Very good. So that was the first reflection. The second one, I asked you in a pipeline MIPS, there are several instructions are active at the same time. This is a very important question. We don't go to the detail of implementing pipeline, but I wanted you to think about it. How could we do that? Because in a pipeline, I told you, one instruction could be in fetch, the other one could be in register file decoding, the other one could be in ALU executing, the other instruction would be in memory, accessing data memory, and the other is accessing the writing in the register file. So we have several instructions using the elements in the pass, and they should overwrite each other. When the next PC comes, then the PC is updated. Therefore, instruction is updated because instruction memory coming out. When instruction is updated, the register file gets different register addresses. When different register addresses are there, then the ALU gets different operands. How could we have all of these things in the same time in our data path? Let's see, what did you write? So name was not there at that time, but she's here. The single component is shared among different instruments and at different pipeline stages during different clock cycles. When this happens, we are lowering it. Instead, pipelining, we can do. You didn't mention the problem and didn't mention the solution. Let's see. Is Akachukwu arrived? Okay, you did. Okay. The problem is that there is only one component being executed at the time, and this might lead to a resource issue where an instruction requires a component at the same time, more delay to the system. A solution is to introduce time scheduling. No, where instructions take turns using the available resources. No, that's not good. Unless by time scheduling you mean something that I will tell you later. This is a hard question. I didn't expect that you have written the right answer. I just wanted you to think about the problem, and if you have any suggestion by yourself or either by using internet and searching through the web. It's okay. Whatever you write here, I like it because you thought about it, you wrote something. So Kevin Lazar. Last time we didn't have. Lazar is here? Yeah. Okay, Lazar, yeah. The possible problem is that there is only one component, hence that one instruction will be occurring with only one task. An example of it would be if there was a adjustment, okay? So a possible strategy would be to further split the single component into multiple smaller instructions following the previous example. We can there turn this one instruction into multiple. You are right about how to do pipelining, but still let me explain my problem. Then maybe you could have some idea what I am talking about. For example, let me bring this. What I mean, we have a data path. In our data path, we have a PC here, then instruction memory, instruction coming here. You see, it's connected. So at the same time, it goes to register file, it goes to reg data 1, reg data 2, and then from here, register value coming out, register 1 coming out, register 2 coming out. But at the same time, it goes to ALU. ALU. And then you see everything is connected. So if you have the next instruction here, then this instruction is changed, then this is changed, then this is changed. So how could we do? How could we have different instructions in our pipe, if we could say it's pipe? Data memory and then write back. How? Did I explain my problem? If you look at this design, everything is connected. What we told before, we told, okay, we do pipelining like laundry, and in the laundry, one instruction is in fetch, the other instruction is in register reading, the other instruction is in execute, the other instruction using memory, and the other instruction writing back register in the register file. This is what we told about pipelining. Now I am asking, how could it be possible? Because if the next instruction comes, then everything is changed. You know, everything is changed. Yes?
You can add registers at the end of every stage.
Oh, very good. Did you write it in your, what is your name?
Arnold.
Arnold, yeah? Okay, perfect. So you see, they are connected. how could we make
No. It's AR and AV.
AR and AV? Arnav, okay. Yes, you see, Arnav wrote, this is possible by separating the CPU into pipeline stages and placing registers at the end of these stages. You see here, what does it mean? It means this. Let me put the registers in blue. So I told you, here is the PC. The PC coming here, and then from here, instruction comes out. So this instruction goes for going to the register file for the next stage. If we put a register here, and this register is clock. And again, we have a register here, and this has the same clock. Again, we have a register here, and this has the same clock. And then we have a register here with the same clock. Then, when one clock comes, the instruction which we have here comes out of the register, goes here. And now we start reading registers. Register file is working. But the registers that have been read before for the previous instructions, they are latched to the register and they go to the next stage. And here, the next instruction doesn't change anything in register until the next clock comes. So putting these registers between the stages, we could make them independent. So here, this register file works independently by these values that came out of the registers. And it doesn't change until the next clock cycle. When the next clock cycle comes, okay, the next instruction comes. And at that time, the registers go to the next stage. And at that time, the value which has been calculated here for the previous instruction goes to the data memory. And at that time, the memory which has been loaded here, it goes for the going back to the register file. So it works. Okay? It was very important. We don't go to the implementation, but for those of you who are doing, I guess you have projects. Who was doing pipeline MIPS in the project? You, okay. So you know that because they're very good. They have to do this. They have to implement this in their project to make it pipeline. Very good. Perfect. So we have, let's go to the course because we are out of time. We have only 4 lectures left, so we have to be fast. Okay, for the lab, during the weekend, I was a little sick. I couldn't record, but I did it today. I uploaded the first section. Let me show you. Content. And I do it the rest for tonight, hopefully. So the video is here, the first video. It is in Verilog implementation module. So you could start looking at that. It is the makeup class for our previous Monday. So everybody should look at that. It is part of the course. But those of you who would like to do the lab 4, the MIPS version of the lab 4, also it is very useful for them because I explain everything here, how to do it in Verilog and how to do the lab 4. So it's there. Sorry about the delay. I got a little problem in the beginning. So now let's go to chapter 3. Let me stop.